Do you like cookies? Do you like quantum mechanics? Do you think that we made up quantum mechanics? And if we made it up, why we made it up? Wait, I want to ask you again. Do you like cookie? If I'm going to give you one cookie, is it gonna be enough for you? Or do you want more? Is it enough? Okay, then what about if I give you half a cookie? Are you still happy? How about 1/10 of a cookie? Probably you're asking yourself, are you still watching a video about challenging quantum mechanics? I have to say yes. Absolutely yes. Do you think I am crazy? Absolutely. If you put these jokes away, you don't know how much cookies and quantum mechanics are close to each other. Let us start the story with why we made up this theory. It was about 1890s, and some German companies that they were making lamp, they went to Planck, one of the physicists at the time, and said, hey, we want a better and more efficient light bulb. Can you help us with that? And if you are a physicist and somebody coming to you from industry asking you from something, probably you're not saying no because money is going to be around and other things. Planck said, yes, let me help you with that. At that time, there were no quantum physics. People around the world and all the physicists were thinking that we know all the things about the world and we can define anything in the world and describe why it's happening. And Max Planck at the time thinking that he can find the best light bulb with the theories and with the definitions that we had at the time. He were thinking that if we are going with higher temperature, we are gonna have more light in the visible range of light. He started experimenting with these basics. He knew if we want to go with visible light and having better lamps, we have to, not lamps but light bulb at the time, we had to block an IR region, we have block UV and have the most of the light that we are emitting from the material that we have in this range, visible range. At the time he was working with electromagnetic theory. In the lab when he was doing the experiments to make something go with higher temperature, it was not acting like what we were believing at the time. If I want to show everything better, the theory that we were believing at the time, it was working like this. If we were going with hotter material, it was having the peak and most emitting part at the part of visible range. And the y-axis here is our intensity or how much a material emitting. Then what he did, like any other experimentalist, he started to go back and not believe on any theory, go with experiment and see what's the meaning of each data that he has. Yeah, he guessed that the whole theory is not working and probably there is something wrong with it. When he tried to go with experiments data, the thing he found out, it was the energy is quantized. But what that means? For that, we have to go back to the first question that I asked. Do you like cookies? And how many cookies are acceptable for you to have? Let's say that we have 6 people, 2 of them not accepting anything less than 3 cookies. That means if you are giving them 2 cookies, they are not accepting that. 2 of them, if you are giving them less than 2 cookies, they are not accepting. That means if you are telling them, do you want cookie? They are saying how many? And you are saying 1. They are saying, nope, it's not for me. I'm not gonna, if it's less than 2, I'm not gonna have it. And 2, the other, they are accepting at least 1 cookie. That means they are okay if you are giving them 1 cookie. But if you are telling to them, do you want half a cookie? They are saying, no, thank you. What if you have 9 cookies? How you have to divide between these people to make most of the people happy? Let's say you have 9 cookies and you want to share it with these people. Let's say first you are going with the first person in the 3 cookies group. You have to give him 3 cookies and you have 6 other cookies. You are going to the other person and 3 more, and you are going to the next group because you want to make most of the people happy. But if you are starting with a group, you have to pay them somehow with cookies. Let's say we are going with the 2 cookie people. You have 3 cookies in total right now. You can give the first person 2 and you will have just and only 1 cookies. And you cannot give to this person. You have to jump from this person and go. And the last cookie that you have to give it to the last person, the person that is accepting at least 1 cookie. Now you made 3 people happy and the other ones are not happy. What if you are starting from the other side and going with the at least 1 cookie group? You are gonna give one of your cookies to this person, the other one to the next one. You will have 1, 2, 3, 4, 5, 6, 7 cookies still. You are going to the 2 cookies group and you are giving it to this person. 2 of your cookies gonna end and finish, 2 other to the next person, and you will have 3 you will pay to this person. And you can see if you are going with this way, you will make 1, 2, 3, 4, 5 people happy. Previously you were just making 4 people happy and you want to make more people happy. And because of that, the second way is a right way. Now let's say these people are a group of wavelengths, and cookies are the energy that we can give them to emit. Let's look at them like this. At least one group gonna be the larger wavelengths, and they need for emitting lower amount of energy to start, and a smaller wavelengths gonna need more energy. You can look at this group like near IR, visible, and UV. For near IR, you need less energy to let them start emitting. For visible, you need more than near IR, and for UV, you need more than visible. And the way that your energy going to distribute toward these wavelengths is, first it's gonna go with the larger wavelengths that needs less amount of energy, then it's gonna go to a smaller wavelength that means they need more energy, because nature somehow like to make more wavelengths happy. This way of distribution of energy is quantized. That means you cannot give less than one part of energy to the near IR, and you cannot give less than 2 part of energy to visible, and you cannot give less than 3 part energy to UV. And this point is a point that every misunderstandings started to growing up in the center of physics. The all quantum theory and all the things about that started from this. Let's dive in quantum theory. If you thought that the relation between quantum and cookies are really odd, what are you thinking about the relation between you or me as an observer and a quantum subject? As I mentioned before Planck, we were thinking that we know everything about the world. We know everything about materials and forces. We thought that the material coming from particles like neutron, proton, and electron, forces coming from fields like electric fields, magnetic field, and all the other things. But the world after Planck got more chaotic. But quantum changed everything. For example, about electron. Quantum acts toward electrons as waves till you are not observing it. But when you are observing the electron, it's gonna be a particle. Did you ever think about with just looking at something, you are changing the property of that? It's like when you have a friend, until you are not looking at him, he's blonde. But at the moment that you are looking at him and observing him, he's changing to have black hairs. It's gonna continue forever, and he's not gonna go back to be blonde anymore. Actually, quantum mechanics is the only, or one of the only theories that the act of measurement is really important toward your result at the end. Quantum mechanics change everything. Instead of having particles and fields, and those particles making other things and fields making the forces, you have two kinds of fields, fermions and bosons. Fermions are more likely to act like particles. They're taking a space, and if you are looking at the world like bunch of strings around, in each of those strings there only can be one fermion at a time. It's like that they are making a vibration through that string, and at each time you can only have one vibration through that string. Like having bunch of rope, if you want to have a fermion somewhere on one of these ropes, you have to make a wave through one of them, and you cannot make two waves at the same time on the same rope. But for fermions, if you have the same kind of rope, you can send as many as bosons as you want through one rope. And those, because two ends of this rope should be technically close in this definition, those two bosons gonna interfere with each other and make a shape like this when you have a standing wave. When you look and seeing something like this, you will have two bosons there. And if you have something like this, it's gonna be one boson around the rope. And if you have something like this, it's gonna be three bosons. And I want to say that the central line that I draw here is more for explanation part, not about there is a rope there still that is not moving. And these are acting like a standing wave in this definition, and there are gonna be something like this. I know there are not ropes through the world everywhere, but with seeing the world through this vision, you can explain fermions and bosons easier. First question probably that it makes your mind busy right now is, what the why we accept something like this? Who can believe these imaginary ropes and strings everywhere? You can ask why we define that many things, why we define fermions and bosons from scratch, and we didn't go with just making the definition that we had from before a little better and not defining everything as any way that we like. But it's better to wait a little. Believe me. Take a deep breath. Keep calm, close your eyes. We are all going to imagine what a quantum field looks like. Not totally, but somehow. Can you visualize a string, and can you see a wave, a sine wave somehow through that string? Let's say that wave that you are imagining at the time is an electron. If we have a function for that wave that you are imagining, we are naming it wave function. Like that sine wave that we said, the wave function of electron that we are imagining at the time is that sine. But don't forget, usually wave functions are not that simple. And instead of a string, electron going to be somewhere around the space that we are naming it orbital. Orbitals are picture of wave function of electron. Did you like it? Yes. Do you want to imagine 2 electrons? Okay. I believe it's gonna be really hard, but let's try all together. Let's close our eyes. For imagining 2 electrons, first we need to imagine 1 electron. The same sine wave that we were looking through the string through the space. Let's go with the same sine function that we were imagining before. This sine function, the wave function of our electron that moving towards the space, makes some positive charges getting close to the sine wave when it's moving around all the space. Open your eyes. Let's look here. Let's say we are starting with here. This sine is a wave function of our electron, and our electron is somewhere here. With this electron moving toward the space, it's taking some positive charge around itself, and after a while, for example, let's say this electron moved from here to here, it taking the other positive charge close to itself, and the other one going back to the place that they've been. I introduced a second electron here. The way that I visualize it here is this another wave function. Why I didn't put this second electron to the same rope as the first electron? Because electrons are fermions, and fermions are particle-like, and particles or fermions cannot be on the same row, and because they are taking a space. Then we have to have the second electron in some place else. Because of that, we cannot imagine something like this. We have to have the second electron somewhere else. But with the movement of this positive charge, the second electron gonna notice this movement, and it's this going to attract it somehow and make this electron move with this first electron that we had. These 2 electrons going to be in a situation that we are naming it entanglement. That means electron 2 and electron 1, they are entangled to each other. That was beautiful, yeah? But there's a catch. I want you, before letting you know about this catch, that promise me that you are not gonna hit yourself or me, alright? Okay, these 2 electrons should not be at the same place. That means, in the way that we explained, it looks like that the electron 1 and 2, both of them are really close range. The real thing is 2 electrons can be entangled, and one of them can be here, the other one can be on the surface of the sun or in another galaxy, and they can stay entangled. I know that seems crazy and not acceptable at all. Take a deep breath. We have to stay healthy if we want to know more about quantum and quantum theory. Or in a better way, if I want to say that, we have to stay calm if we want to know how much we don't understand this theory. 1970s is a year that we found out we didn't define enough variable for quantum theory. Physicists all came together. They said, what we have to do? Nobody had any idea. At the gathering, there was a heavy silence. Suddenly, somebody said, quarks. I'm sure till now, till this day, that he didn't want to define something. And he just wanted to show how good he is in making sound of frog. But if you be around a lot of physicists and nobody talking, and you suddenly making sound of frog and nobody laughing about it, and you just wanted to make silence go away and make people laugh, I'm sure that if it's been you too, probably you were going to define something. You were going to act in a way that I meant something by quark. And you have to know that in quantum there is a trend to defining something, and because of that, probably if you be at the same situation, you were going to define something too. That's the real story with Maury Gell-Mann. The definition were about neutron and proton, both made of quarks. The sound of frog. Yeah. Probably in your mind right now you are asking yourself that how, if you are not going with the pro or pro plus version of quarks, you will have 2 types of quarks, up and down. For the up one, you have the charge of +2/3. For down, you have -1/3 of a charge. Then if you are going with this definition for quarks, the basic version, proton gonna be 2 up plus 1 down, and the total gonna be +1 charge, and neutron gonna be 1 up and 2 down, and the total gonna be 0. What? You have a question? Yeah, I can hear you. You want to know then what is electron? The negative charge. Is it gonna be 3 down quark? I have to say you are wrong. Actually, quarks, the basic version, is defined by up and down quark, and electron and neutrinos are under another category, and the name is leptons. The more interesting thing is, as proton made by up and down quarks, neutron made of up and down, electron with a negative charge is a lepton by itself, and neutrinos are electrons without charge. But you have to know that these 4 things that I wrote here are not the only members of leptons and quark family. In quark family, we have charm and strange, and each of these are the heavier cousins of up and down. And we have top and bottom quarks that they are heavier cousins of charm and strange. For leptons family, we have electron and neutrinos, or we can name neutrinos as electron neutrinos. We have heavier cousins of muon and muon neutrinos that they are heavier cousins of electron neutrinos. We have tau and tau neutrinos that they are heavier cousins of muon and muon neutrinos. Maybe yes, are there more? I have to say probably yes. And if not, for sure, in quantum always we can define. Don't worry at all. And maybe now you're asking yourself that why we have or why we need bosons. Fermions are interacting with each other through bosonic fields. Bosonic fields are like electrical fields, magnetic field, gravitational field, and nuclear field. And these are making electrical force, magnetic force, gravitational force, and nuclear weak and strong force, and a lot more. Using at least right now we have everything that we need about quantum theory, or we are at least agreeing there probably are a lot of fermions and bosons, only 2 kind of fields, and whatever else we are looking at through universe, it's gonna be under these 2 definitions, and these 2 kind of fields gonna define how particles are made and how they're interacting with each other. Nope, if you are thinking like that, we are not at the same page at least. Maybe you and me be at the same page, but we are not at the same page with quantum physicists. Do you know what is Higgs? Higgs is not fermion and at the same time is not boson. Higgs is a part of the field and it's all over the space. All the other particles going to swim through Higgs. Both quarks and bosons can feel influence of Higgs. Apparently at 2012, Higgs boson found and showed to us that Higgs field is real. Who am I to question quantum and quantum field theory? But wait a minute. It's enough. I know quantum theory and quantum field theory and all the quantum other theories can define everything is happening in the experimental part of our research at the time, but can't you remember ether? Higgs make me to remember the part of history that Einstein was talking about. All through the universe, everywhere we have ether, and all the things like sun, any other star, earth, every other thing, they're swimming through ether. And he was saying that why light can go through space and move in the space. That was the medium that light needed for that. Because there was some medium around the world, all over the world, by definition that Einstein were giving us, then the speed of light should not be same everywhere in the universe. People did experiments and they saw that the speed of light everywhere same as any other way. After the experiments happened, people cancel out the theory of ether, and you have to know something. Doing the experiment in that magnitude of space is so much easier than doing experiments with quantum materials and particles. The way that Higgs looks like ether for me make me feel that something is wrong. Maybe Higgs at the time filling a hole that we have in our definitions and the way that we defined quantum theory and quantum theory field, or maybe not. It feels odd. And the other thing that makes me to continue this fear of Higgs that I have is at the time that we were defining everything by ether and other things, every other experiment's result were okay with the theory that we had till we found out the speed of light is same everywhere. And Higgs giving me the same feeling, that okay, everything is good till now, but what if a day we waking up and seeing one result of our experiments not okay with the definition that we have? Actually, one of the things that not making sense with quantum theory right at the time is dark matter. At the time, quantum theory researchers, they cannot describe dark matter with what we know about quantum theory till now, and they are mostly optimistic that they didn't define enough particles to see why dark matter exists. And they're saying probably in theory, in future, if we can find enough particles and fermions and bosons that describing the world, and if we are getting closer to that point to describing everything, probably dark matter gonna be one of the things that we are gonna describe in future, and that's lack of the knowledge that we have at the time. But maybe the theory that's going to define dark matter as a part of the whole universe is gonna be totally different from what we know at the time as a quantum theory, because the same thing happened about 1890s when a company that making lamps went to Planck and said, "Hey Planck, can you make us better lamp?" And suddenly we found out, oh my god, nothing making sense anymore. And we have to know that each theory that we have at the time, they are making a lot of changes about the way that we are looking toward our even day-to-day life. But maybe in near future we have another impactful theory that we don't know, let's name it theory X, that can define everything. And quantum theory till now is the best theory that we ever had, and it's describing a lot of things. One of the other things that I have to mention that I forgot is in quantum field theory and in quantum theory, we are considering amount of quarks in the world conserved. Like if you want to change a neutron through radioactive decay to something else, at least you will have proton and some other things. And the proton is a quark part, because quarks, neutron and protons are the only things that made of quarks. You can't suddenly change a neutron or proton. That's something that has only fermions. You have to have quark because the amount of quark in the universe is conserved. And usually besides some fermions, all the other things gonna decay to a shape as quarks, as proton and neutron, and leptons, electron and neutrinos, with some bosonic field, and the whole thing make you and me as a human, not a lot of other things that quantum theory defining usually. And maybe you're asking how we know dark matter exists, because quantum physicists believes that they can see the interaction of materials with something, even if they don't know what is that something. For example, with dark matter, they can see that your body even interacting with something that they don't know, and they can find and figure out that interaction. Unfortunately, we don't know what it is, and we cannot describe it with quantum and quantum field theory. And don't forget why we are trying to define different kinds of theories in physics. The only reason is we like to know how everything works, and we want in future to have a theory of everything that describing every other thing with the same knowledge that we have. For example, if we are going enough back through the history, you can see electric force, gravity force, and all the other things are defining by themselves, and they are not related to each other. But right now with quantum, we are totally understanding electromagnetism, and we are trying to define all the other forces with the same knowledge that we have as a quantum theory. And this try happening through different kind of symmetry that we are gonna try to put electromagnetism, for example, to nuclear force or to gravitational force. Photons are describing electromagnetism, and the mass of photon is 0. Through our definition and the symmetry, we could define gravitons, and gravitons are the particles that are making gravity and gravitational force. Their mass is 0 too. This comes from symmetry that we found out between gravitational force and electromagnetism, as right now we don't have enough technology and energy to make graviton in our labs. We know photons and we define gravitons in a way that is describing everything somehow in a right way. The problem happening when we want to use the same kind of symmetry to go from photons or gravitons to something that can define nuclear force, both a strong and weak part of it. Not like nuclear force, both electromagnetism and gravity can affect in a long range, but nuclear force is a short range force. We know that when we have a long range force, that means that you have a particle that the mass of it is equal to 0. And when you don't have it, you don't have any particle that the mass is gonna be 0. And the problem happening when you want to have a symmetry to go from photon with 0 mass to something in a nuclear force and define it, and it doesn't have mass equal to 0. You cannot use symmetry for something like that. But as you know, quantum physicists always have something in their head to show it to you, and this time is nature trying to let you not see what's going on with nuclear force, tries to hide it when it's going to longer range. Then with this way of thinking, you can have a massless particle that can define nuclear force, but it gets hidden by the nature. What? You're asking how nature can hide something? Don't worry. Let me bring back the hat of quantum physicist. For a strong nuclear force, the way that nature hiding the nuclear force from you for longer range is the gluons that are making this strong nuclear force happening. They are all in a circle, and if you are defining them like this, it's like that they're force bumping into each other and makes zero force at the end when you are going farther from this circle. It looks like that you have a lot of force that are going from the same center, and all of them has the same amount of force. This gonna be equal to zero force when you are looking it from outside. For the weak nuclear force, we have to have our man of the time, man of the scenes, Mr. Higgs. This actor this time gonna act in a way that is gonna hide the weak nuclear force. Yeah, that's the same Higgs that's all over the space everywhere. Sometimes when I'm thinking about quantum, I'm feeling empty. I'm feeling that there is nothing that can fill my life and fill the holes that I'm looking here and there. But at the same time, you can go to a quantum physicist and probably they will find a definition for you if you feel like me. As Carol from Johns Hopkins University saying,
but we know it's not the final answer. You'll find zero physicists today saying that we have the complete theory. They might have different opinions about how close we are to having the complete theory. There's several obvious reasons why we know we don't have the complete theory. Dark matter in the universe is the most obvious experimental result.
We talked enough about quantum theory and other things under it. Let's talk about quantum computing. Have you ever heard of quantum computing? Probably if you are looking at quantum computer news at the time, about a year ago, you would hear about something like the new quantum computer of Microsoft, or maybe nowadays you are looking at some videos that they are talking if we can do AI and AI training with quantum computers, we would have wonderful and really better LLMs in future. And that's when we have to be afraid of AI. But what is quantum computer? Is it a magical box giving us the answer of all the questions that we have? Let's start with an example and go step by step together to see what are quantum computers and what's the differences between a quantum computer and a regular computer. Let's say the problem that we are gonna go through is gonna be like that we have a set of number from 1 to 10, and we have a problem that one of these numbers are the possible answer for that problem. We don't know which of them. Let's see how CPU, regular computer, working towards solving this problem. For the regular computer, you have to put the input inside to the computer. After computer solving this problem, if the number that you are putting into it be the right answer, it's gonna give you back 1, and if it's not gonna be the right answer, it's gonna give you back 0. And the 1 there is not the same 1 as this. The 1 that means true, and 0 that means false. The way that you have to handle this with the regular computer is to feed each of these numbers with whatever system that you like to this CPU. For example, you can say 1 be the input, go to the CPU and give you 0 or 1. 2 be the input, go to the CPU, give you false or true. And it's going on till you feed the right number for the problem that we have here. And it's giving you 1. And whenever it gives you 1, you're saying, okay, that's my answer. When you are looking forward to see what was the input, you will find the answer that you are looking for. We have 10 different numbers. That means our n is equal to 10. And for finding the answer, the average time that we have to try to feed the CPU to have the right answer is n over 2. That means if we are probably with whatever way that we like, for example, feeding 1, 4, 3, 5, 6 and go on, and one time going with 1, 2, 3, 4, 5, 6, one time going with 10, 9, 8, 7, 6 and going back, and any other way that you want to feed this CPU, the average amount of number that you have to try to have the right answer is n over 2. That means your computation and process of seeing which of these inputs is the right answer for your problem is related to n and multiplied by 1 over 2. On the other hand, for quantum computer, there is no CPU. Instead of CPU, we have qubits. And these qubits gonna do the process for you somehow. You have to somehow feed your data toward this quantum computer and have the answer. What do you think about how many tries we have to do with a quantum computer to have the right answer? As we saw, for a regular computer is about n over 2 times that you have to try to have the right answer. But how about for quantum computer? That's one of the interesting questions that you usually can ask someone when you're first talking about quantum computer to them. Do you think the amount of tries that we have to do to have the answer of the problem that we define gonna relate it to root of n, gonna relate it to logarithm of root of n, gonna relate it to logarithm of logarithm of root of n, or gonna relate it to 1? And what is 1 mean? That means the way that we are handling this problem with quantum computer is not related to how many numbers we have. For example, if we have 10 numbers or 100 number or 1000 number, it's not related to them. It's gonna be a constant number, and whatever you are feeding the quantum computer, it's gonna give you as a same amount of time, and it doesn't matter how many input you have. The channel 3 blue 1 brown tried to ask the same question from different group of people, like people on YouTube, MIT students, and mostly people answered by 1. That means the time that it's taking to you have the answer from quantum computer is not related to how many numbers you have as an input. If I want to describe it better, that means this set of number that we have from 1 to 10, if you're saying the answer is 1 and the time that it takes that quantum computer giving us the output is not related to how many numbers we have, it's like that we are feeding all these numbers at the same time in a way that it seems like parallel to this quantum computer, and it gives us the output of all these possible input at the same time. Till now I didn't explain to you what is quantum computer and how it's working. Let's go step by step and maybe we change our mind about the answer that you had. Let's continue with this flowchart somehow. For a regular computer, we have a state. The input that we are feeding to our CPU is in a state that we can measure and we can see. What I mean by we can see and we can measure, if we have number 10 and we are gonna feed it to the CPU, there is a voltage that we can put on our circuit in the CPU that means 10 and nothing else. The regular computer has circuits and voltage, and the value if it's giving you in output, it's deterministic value and you can measure it. But for quantum computer, you are not feeding it an state, you are feeding it state vector. And what is a state vector? We are gonna talk more about it, don't panic. But the thing is, you cannot see a state vector. It's not something like voltage that you are implied to a circuit in your CPU to you can see it and say, okay, here we have this voltage. And the problem is when you have a quantum computer without any algorithm, the value that you are measuring from your qubit is mostly random. For explaining this part better, I want to make the problem that we talked about much easier. Instead of having numbers from 0 to 10, let's say we have numbers 0 and 1, and we want to see which of them is the right answer for our problem. The way our regular CPU working is that you are putting 0 into our computer and it gives you true or false. After that, you are giving 1 to the computer, it gives you again true or false. Only one of these input can be true, and because we have two options, the other one gonna be the false one. But for qubit it's not like this. If you have only 0 and 1, the way it's happening is you will feed it with a state vector, and this state vector is a combination of 0 and 1 at the same time. You may ask, right now we are feeding all the data all together to the qubit, and you are right somehow, because we are feeding the state vector of two possible input to our qubit. But does it mean that all the process happening in a parallel way? No. Not actually. We have to describe more things to reach the place that know how quantum computers working. At the time, I can tell you that the process inside the qubit is not parallel, but at the same time, it's not individual too. That means you are not feeding the quantum computer by each of your input step by step like the CPU. The problem with quantum computers, as the name is coming for the processor here, the name is qubit, it's quantum bit. You have to know from previous sections, quantum considering a really close relation between the observer and the quantum material. That means after you are feeding your qubit with the right state vector that has all your inputs, you will have an answer that is a combination of all inputs all together. Then you may ask, what if, for example, we have an output like this and we are observing this system again and again till we know which of these state coming with higher probability. For example, let's say you are trying to measure 10 times what is inside your qubit, and 8 out of 9 you will get 1, and 2 times you will get 0. And you are saying probably with yourself right now that okay, the 1 is answer and the 1 is the right answer. There are two problems with the way that you described your solution. First of all, after measuring what is inside our qubit, you as an observer making an effect on the qubit that you have. That means your state can collapse to something like this, or it can collapse to something like this. That means it has 100% of 0 or 100% of y. And after you did your measurement, you cannot go back to the initial state that we had that was a combination of 0 and 1. And the other thing, if you don't have a right algorithm to process your data, whenever you are running this qubit, you will have different probability density of your possible output. That means the first time it can be something like this, second time can be something like this, third time something like this, and it is random to see which of them gonna be higher in probability distribution. The other problem with the solution that you introduce is, do you think that if one has the highest probability and you don't have any specific algorithm here in your qubit to affect an output before you read it, is one the right answer? Or if third time you have more zero is the answer? Or what you have to do? Beside the qubit, and the wonderful thing, it can have all the input states at the same time. Problem with this is you have to have the right algorithm inside your qubit that can affect on your output before you're reading it. Because each time, if you don't have any algorithm and you're feeding bunch of data to qubit, it's giving you a random probability distribution. You probably noticed that I'm writing the state vector in something like this. I want to introduce you to chit. If you have one of these and you can put just one number in it, that means you have one qubit. And the meaning of one qubit, that means it can have 2 to the power of 1 output type. If you have 2 places in your chit, you will have 2 to the power of 2 option for your out. And if you have 3, 2 to the power of 3, and if you have n, 2 to the power of n. And as much as you have more qubit, that means you can feed your quantum processor with more data. One qubit is like this. It has one place inside of it that can have the option of 0 and 1 at the same time. The way that I want you to look at it is, we have y-axis as 1 and x as 0, and this is our state vector. And because x and y can be any number at the time, you can go in a circle and each of these can be your state vector. Now we understand more about what is a state vector in the simplest way ever. But how the algorithms works, and if we are feeding this vector to our quantum computer, how it's gonna affect our vector state to give us the right output. Because as we talked till now, whatever answer it gives us at the time is gonna be a random probability distribution of all the output options. And the other thing we understood is, if we are feeding this state vector to our qubit, whatever answer it gives us, and even if the probability distribution of one of them be higher than the other, and if the probability of one of these options happening more than the other, is still, it doesn't mean that it's the right answer. One other question probably make your brain busy at the time is, what is probability distribution and where it's coming from? I have to let you know that if we have this as our state vector, these numbers x and y, they are multiplying 0 and 1. If we are making them to the power of 2, the magnitude of them to the power of 2, we will have probability distribution of each of these two. The other important thing about quantum physics is, if we are adding probability of each output, the number should be equal to 1 or 100%. And that's because something should happen. You cannot feed your quantum computer and nothing happening. If we are making a summary about what we learned till now, is about the state. For the bit, you will have a state of 0 or 1, and you are feeding it to your bit. As an observer, you will observe 0 or 1 as a result in a system of 2 possible input of 0 and 1. And this 0 and 1 and this 0 and 1 are not same. These two are the input, these two are true or false. And for your qubit, you have a vector state, and you will have 0 or 1 as an output when you looking at your qubit. Again, for summarizing everything better, if you are feeding the vector state to your qubit, you will have something like this. And if you have higher probability, and if you don't have any algorithm in your processor of quantum computer, this doesn't mean that if you have higher probability, that means this is the right answer. But for your bit, you are feeding it with 1. it gives you true or false, and you are giving it 0 and it gives you true or false. And one of them are true, the other one is false. And when you are observing your quantum computer output here, you are collapsing this probability distribution to one of these probability distribution. You are reading 0 or 1, and after that it's not gonna go back to this state anymore, because as an observer you made a change. Regular computer give you 0 or 1 as an answer, true or false, but quantum computer gives you a combination of your inputs till you didn't observe. When you are observing it, it's changing to just one of the input, and it doesn't mean that it's gonna be the right answer. How we can make the quantum computer give us in the output the right answer with the highest probability? Actually, for that we have to look back to the regular computer. For regular computer, like what you are watching this video on it, like your laptop, mobile, iPad, and any other thing, they are using some logical gates like AND, or, not, nor, probably some other gates, and these are gonna affect your input and gives you true or false. If you don't have this kind of logic gates and you're feeding your regular computer with some voltage, it's not gonna give you any valuable answer. That means it's gonna give you random answer. Then we have to define something as quantum gates. Quantum gates are the same logic gates that we have for our regular computer, but in quantum world. And instead of affecting your input, they are gonna affect on your state vector. And usually they like rotations or flipping towards one of axis. Like here, if we have the initial state vector, we can flip it on y-axis and you have this. You can flip it on x-axis, it's gonna be like this, or you can flip it on both of them at the same time and you can have something like this. And this is the way that we are influencing our state vector to make the right answer have the highest probability. With having bunch of gates together, you are gonna make a quantum algorithm, and that quantum algorithm gonna make your right answer with highest probability. I want to go back to the other question that you asked, how we are affecting the quantum computer output to have the right answer with highest probability. Let's go step by step and see what's going on. The algorithm is going to help us here to find out which of these answer is the right answer. It's working like this. At first you are feeding it with a state vector and it will give you an output like this. 0 has the probability of x to the power of 2, 1 has y to the power of 2, each of the magnitude of those numbers. The first step of Groover is it's gonna edit this to the way that x to the power of 2 and y to the power of 2 be the same amount. And we don't have to forget that the summation of these two numbers gonna be always 1 or 100%. After this step, I drew two different states. Let's say in the top one is the answer. What it's doing is multiplying y by a negative sign, and the magnitude gonna stay the same. And if 0 is the right answer, is multiplying a negative 1 to the x. And after this, it's gonna act in a way to the one that we multiplied a negative sign to it to amplify it. And the new probability of 0 is gonna be higher if 0 be the answer here, and if 1 be the answer, y to the power of 2 gonna be bigger and bigger. And these steps gonna happen again and again till you have about all of the probability distribution for 0 if 0 be the right answer, and for 1 if 1 be the right answer. I didn't specify that 1 or 0 is the answer, and I explained it for each of them to just show how it's working. This time let's go with another way that we are visualizing our state vector as a vector. Let's say this is our state vector. The output that our quantum computer giving to us is gonna be x multiplied by 0 state plus y multiplied by 1 state, and it's gonna be our state vector. I'm gonna first do it in a way that 1 is the answer and explain it step by step, and after that going and just showing to you what if 0 is the answer. If the 1 be the answer, it's gonna multiply a negative sign to y. That means our sign going to be x 0 plus negative y 1. And if we are visualizing it here, that means x gonna stay at the same place, but y going to change the direction to negative y. And here is our new state vector. I just want to mention that the angle that we have here is the same angle that we have here. The next step of this algorithm is if our initial vector be here, and we are not gonna forget the place of our initial vector, it's gonna flip it toward this vector. That means this right now is theta plus theta 2 theta, it's gonna flip it in a way that the answer gonna be here, and it's gonna be 2 theta from the first initial state. And if we are drawing that, it's gonna be 3 theta, okay? Because this is 1 theta, this is 2 theta, from 0 we have 3 theta. I'm gonna do the next step this side because I don't have any space there. We are going back to this step. 1 is the right answer, then you have to flip the sign of y. That means your state gonna be here with an angle of 3 theta from 0. Initial vector is gonna be here with an angle of theta. And the step after flipping, it's gonna be to flipping toward the initial one. That means right now we have an angle of 4 theta. You have to go with an angle of 4 theta to your initial one, somewhere here, 4 theta, and with 0, you will make 5 theta. I know that seems a little complex, but as you can see, it's getting closer and closer, and this is with considering 1 is our right answer. I could draw everything back, but if we are considering 0 be the right answer, and if we are just flipping these two and doing the same steps, you can see that it's getting closer and closer to 0. It's gonna get that close to the right answer that alpha gonna go to 90 degrees, and that means that all our probability going to be in the direction of the right answer. 0 or 1, doesn't matter. I want to tell you that I didn't explain anything in the imaginary part because Groover's algorithm not affecting on imaginary part, and it's just affecting on the real part of the vector. And yeah, for quantum computers and quantum things, we are having an imaginary part of the vector too. That makes everything more complex, and it's using to make the difference between the right and wrong answer when you have more complex problems. And with what I explained, you can see right now that maybe at first you are thinking that quantum computer doing processes on all the input all together. But when we went through the steps, you can see it doing the processes in its own way, with quantum gates and algorithm. And the question that I asked you at the first of this section, the amount of try that we have to do for having the answer for a quantum computer, it's gonna relate to n or no, and I think mostly you said no, you chose 1 as your answer. But as you can see here, we have a relation with our n. I didn't go with higher amount of n to show it to you, but as we are going with more than 2 input, we are going with more than 3-dimensional a state vector, and it's harder to visualize. I want you to accept from me that the amount of steps that you need to reach to the answer for the quantum computer is gonna relate to root of n, and the relation gonna be root of n multiplied by pi over 4, and we can go through it in another video later. But what is the problem with quantum computers? Actually, I want to mention one of the videos that I saw about this in the channel Looking Glass Universe. If I'm not saying the name wrong, there is a video about why I left quantum computing research, and probably said it before because it has millions of views. She's saying why she left quantum computing research is because there are a lot of innovation happening at the side of quantum computers, but not in the side of algorithm. And as you saw, we looked at the really simple problem, but at the same time we need to have more algorithms to do more things. For example, there is another problem that can give you the factorial part of a big number, and the name is Shor's algorithm, and it's working at the time with quantum computers, and Groover's working at the same time too. But there are a lot of other problems that we don't have any way to make that state vector of output in a way that the highest probability be the right answer. And beside that, you have to know we have quantum computer noise, and we have different kind of quantum computers. That means sometimes some problems working with some kind of quantum computers but not the others. In the side of theory, maybe we have a lot of algorithm that working at the time. But if you want to put them in quantum computer and see if you can have the right answer or no, unfortunately mostly they are not giving you the right answer. I suggest you to go and watch her video if you didn't see, because probably you can see what's going on, what are the problems and limitations for quantum computing at the time. Again, let's go back to the question, is quantum computer faster than regular computer? As you can see here, for the problem that we talked, the amount of try that you have to do in average is n over 2, but for quantum computer is pi over 4 multiplied by root of n. And if you have 0 variables, not comparable. If you have 1, you can see that regular computer computer is faster, if you have 2 regular computer is faster, but if you have 3 numbers, the quantum computer are going to be faster, and after that it's going to be the same. Today we learned about quantum computing and how it's working, and learned about quantum theory and where it's coming from and all the other things. The relationship between quantum and cookies and observers, all we talked about. But there are a lot more to talk about quantum computer and other part of physics. I hope you enjoyed this video. Please let me know about what you're thinking in the comment. First of all, I want to mention I'm not a quantum physicist. I'm working in another side of physics, but at the same time, it was really interesting for myself to know more about these things. We just scratched the surface of quantum theory, quantum computing, and all these things, and we can go through it more together if you want to. Let me know if you like these things. Like and subscribe is the way that I can understand this. Did we made up quantum theory? Yeah, we made up any other science that you are looking at too, but it's working somehow, and that's the important part. Hopefully we can improve it in future, but at the same time, that's a wonderful theory that we have at the time. Thank you for watching. See you next time.